Welcome. My name is Dr. Ren, and welcome to the AP Calculus open house. A little bit about me. I have my PhD in curriculum and instruction with a minor in mathematics. I also have a master's in math. My undergrad is in mathematics, in applied math. I taught in the university level first, and then I moved to teach in high school. I have over 10 years of experience teaching. I have taught geometry, algebra 2, precalculus, calculus, BC, multivariable calculus. I'm currently teaching multivariable calculus and calculus BC at Dulles High School. I don't know if you have any questions about me. Please feel free to unmute yourself and ask any questions at any time. Well, the class that we'll have, it's going to start next Sunday, September 10th through December 10th. The prerequisite is that students, they already took pre-calculus, and maybe they are most likely enrolling to either AP Calculus AB or AP Calculus BC. The idea is that this class helps students to, prepare them for the AP Calculus test. Remember that calculus is, especially calculus BC, is the first semester is calculus 1 and the second semester is calculus 2. So during the fall, we would be focusing in the first part, which is calculus 1. We would be going over, well, I'll go into the next slide. So from limits up to pretty much solids of revolution. We would be covering, if you are using the textbook Larson, from chapter 1 through 7. If you are using Stewart, from chapter 1 to 8. The time of our meetings, it would be from 1 to 3 p.m. Every Sunday. The weekly homework, it will be assigned, and I'll post the keys and everything for the homework and the notes. It will take between 45 and 90 minutes to complete. The idea is that the student is taking, obviously, AP Calculus AB or BC during the school year. So if they have questions from class and things like that, they can obviously ask questions regarding that. So I can support them with the class. The AP Calculus exam format is pretty much, it has two sections, the multiple choice and the free response. The multiple choice will be 45 minutes, 45 questions. First, they are going to have the 30 questions that are non-calculator, and then the 15 questions that are with calculator. They give them 30 questions for 1 hour with no calculator, and then after that, the students, they move on to the calculator section, which are 15 questions in 45 minutes. After that, they move on to the free response part of the test, and they start with the calculator section, which are 2 free response questions, and students will have 30 minutes working on those 2 questions. After those 2 free response questions, it comes the end of the test, which is the 4 free response questions with no calculator. The College Board gives them 1 hour to complete those 4 questions. Those questions are pretty interesting. That's going to be the main focus, that they can give a really, really good idea of the questions over on the free response no calculator. Because usually that's the most difficult part of the test, according to, College Board. So what topics will be covered during AB and BC? AB is pretty much limits and continuity, differentiation, okay, the definition, all the properties, all the formulas. After that, applications of differentiation using the chain rule, implicit differentiation, inverse functions, natural log, exponential. And then Unit 4 moves on into conceptual applications of differentiation, like concavity, first derivative test, second derivative test, solving more application problems regarding differentiation. Then Unit 5 is more analytical applications of differentiation, such as the mean value theorem, extreme value theorem, sketching graphs, how to solve optimization problems, and behaviors of implicit relations. For calculus AB, still they learn all integration. Not all integration, it's only use substitution and the accumulation of change using the fundamental theorem of calculus. What else? They also learn about the indefinite integrals for AB and the properties of basic integration techniques. Unit 7 is going to be differential equations, which includes slope fields, how to sketch the curves through slope fields, deriving and applying and model logistic growth and exponential functions. And the last part for AB, it will be Unit 8, which is applications of integration, such as the average value and also accumulation problems relating volumes and solids of revolution, cross sections, the disk method, the washer method, and all those 3D accumulation problems. So that will be for Unit 8. So the idea is that this semester we end up around Unit 8. So I don't know if you have any questions about that. Feel free to unmute yourself if you have any questions. What else? The additional topics that Calculus BC covers that AB does not cover, that this would be the following semester, it would be during the spring semester, it would be extra techniques of integration, such as integration by parts, partial fractions, and all of that. Then in differential equations, AB doesn't cover Euler's method and all the logistic models of differential equations. They only cover like basic ones. For Unit 8, the extra part that BC also covers is the arc length and distance traveled along the smooth curve. And obviously Unit 9 and Unit 10, they are completely for AP Calculus BC, which that would be all of this part, it would be for the spring semester. It would be finding derivatives of parametric functions, vector value functions, area polar equations, finding the derivatives using polar coordinates. All the parametric and polars is included there. In addition, for Calculus BC, it would be all the infinite series and sequences, also Taylor polynomials, Maclaurin polynomials, the Lagrange error bound, and all of that would be part of Unit 10. So that would be during spring. Then what would we cover the semester? Specifically the semester, it would be limits and continuity, which is pretty much Unit 1. Then the fundamental theorem of calculus, which is, I believe it's Unit 4. Basically, we're going to cover everything from Unit 1 through Unit 8, except the parts that are for BC only. For BC only, it would be during the spring semester. So we would cover curve sketching, rate of change problems, optimization, mean value theorem, intermediate value theorem, all the definitions of derivative and all the formulas regarding differentiation techniques. What else? Definite integration via use substitution and transcendental functions, the formulas, pretty much that would be included. I would include also how to apply all of this in the calculator, specifically speaking in the CAS calculator. Yeah, I don't know if you have any questions, please feel free to ask any questions that you might have. Let's see if anybody has questions. Okay, so let's see if anybody has any questions. Okay. If you have any other questions, remember that the hours of operations for Momentum are Sunday through Friday, 11 a.m. to 5 p.m. Central Time. The Saturdays they are closed, but you can always reach them via email. The email is over there in case that you have questions during other hours. Yeah, thank you. I don't know if you have any more questions or concerns? Okay, let me see, questions. Screen sharing. Let me see any questions that you might have. Okay. So I'll start with one of the mini lessons here. Let's see. Okay, so I'm going to do the introduction for the first topic, so you can see the way that I teach and everything. So let me share my screen and let me put my document camera close. Normal camera and let me share my screen and escape this part. Sorry about that. Start my document camera. Okay. Okay, so my document camera is there. Zoom in, otherwise you will not be able to see. Okay, so let's start with the first topic that we have for calculus. Okay, so which is limits. Before we introduce limits, I would like you to recall what were the end behavior back in pre-calculus. So in pre-calculus, what you cover is that you were analyzing the end behavior of each function. So if we call this function f, and you have that this function is the one that you see over here, since you are in the computer, let me make it with color so you can see clearly the behavior of the situation. Okay, so you can see that function f over there, and you have this function. The end behavior, if you remember, it's pretty much the arrows that you have here and here. So what we know in this equation is as x approaches to infinity here, what do you have? In this equation, since we call this function f of x is going to approach to what? Since when x is going to infinity, what's happening to f of x? It's going down. It means that that's going to negative infinity. So this is the end behavior of your function. Similarly, you can think that as x is going to negative infinity, meaning going to the left side, what's happening? When it's going to the left, what do you see that it's happening to the arrow? It's going up. This means that f of x is approaching to positive infinity. Okay, so you can see here the behavior of this graph. So when we call approaching, f of x approaching, we're indirectly talking about the limit. Let's look at another example so you can see that it's pretty fun. Okay, so this graph that you have over here, that let me use my highlighters so you can clearly see it from there. Okay, so you have that it has two pieces, this graph. So let's analyze as x approaches to infinity. When x approaches to infinity, remember, you are going to the right. What's happening to this arrow? You can see that here, we can see that this line, okay, this function is not crossing a line that it's here, invisible line. And you can see that this line, okay, since this is the origin and this is 1 unit, it's approaching to 1. Do you see the asymptote there? Y equals 1, so we have an horizontal asymptote. Y equals 1 over there, meaning f of x is getting closer and closer to 1, okay, or approaching 1, okay, on this side. You see it? It's never going to cross the 1, okay? Similarly, as x approaches to negative infinity, let's analyze when it's going to the left. You move here to the left, and what's happening there? You can see that it's getting closer and closer to, again, the number 1. So what this is telling you is that the function f of x, and let's call it f, okay, is approaching to 1 as well. Okay, so what is the limit? Okay, as you can see, it's something regarding with the function approaching, right, to a certain number. So the concept, okay, the concept of a function, okay, approaching a certain value or specific value, okay, is called a limit. And this is going to be the beginning of our calculus class, okay? So with this being said, now you know the meaning of a limit. What we're going to do here is we're going to start using the notation in a more elegant way than what you learn in pre-calculus. So given that you have a function, let's call it f of x, the limit L, okay, which is a number, of f of x as x approaches to c, it can be written as follows. You are going to say the limit when x approaches to c, and you write this notation of f of x is going to give you L, okay? So this is the notation that we use. This is telling you that you are finding the limit when x approaches to c of the function f of x, and this is going to be equal to L, given that L is a number, okay? So you can see that it's pretty user-friendly, and actually it's less writing than this, what you were doing in pre-calculus, okay? So honestly, it's more fun with this notation that we have over here, okay? So let's write now the end behavior of each function instead of like what you were doing back in pre-calculus using this new notation that we just learned, okay? So you can see that here we have something that looks like a parabola, okay? That actually it's a parabola, okay? So you can see there, and I'm using the highlighter so it's clear for you where's the graph, right? Okay, so what can we say here? The limit when x approaches to positive infinity, okay, let's call this function f, okay, because we're very original, okay, of f of x, what's happening? Okay, so when my x is going to the right without a bound, what's happening to the arrow? It's going down. Down where? Well, up to negative infinity, okay? So this is a new notation that we have. So that tells you that as x approaches to infinity, f of x approaches to negative infinity. Similarly, using the same function that we have over here, we have that the limit when x approaches to negative infinity, meaning we're looking when my function is going to the left, okay? So of f of x, what's happening here, this function is going down again. So this is going also to negative infinity, okay? So as you can see, there's no rule, right? You always need to look at the behavior of each function individually to conclude, okay? So let's look at another 2 examples. Let's call this one G, okay? So this one is a little bit more blurry, okay? So let me graph it so you can see it, okay? So you can see there the function because it's very close to the y-axis, that part, and it's kind of like not clear. So now with the colors, we make it clear, okay? So here we're going to analyze when the limit approaches, let's say, to positive infinity first of g of x. So over here, what you have is that you're looking when the x is going to the right. So what's going on? It's going up. So without a bound, meaning this is going to be positive infinity. Similarly, when you look at the limit, when x approaches to negative infinity of g of x, meaning we're going to look at the function when it's going to, the x is going to the left, okay? So what's happening here? It's going down, meaning it's going to negative infinity, okay? Let's look at another problem over here so you can see what's going on with that. Let me also use the color so you can see here what's going on, so you can get the idea. So over here you can see the arrows over there. So let's start with the limit when x approaches to positive infinity, and let's call this function h, okay? So the limit when x approaches to infinity of h of x, what's going on? We're going to look when the x is going to the right, okay? So it's going up, so this is going to be positive infinity. Similarly, now we're going to analyze when the limit of x approaches to negative infinity of h of x. And then what's going on here? Look, the behavior when it's going to the left, and you can see that it's going also to positive infinity, okay? So that's how we can find, and we can write now the end behavior with our new notation, okay? So I don't know if you want to do 3 more, or we can move on to the next topic. Okay, since this is just a demonstration, I'm going to move to the next topic, okay? So let's look at some notations here, okay? So you can see, so you're going to tell me now, oh, so are limits always going to infinity or negative infinity? No, most of the time, well, not most of the time, but sometimes the limits go to a specific value. So what if c is a specific value, not infinities? If c is a specific value, then the limit is the value in which x is approaching from either side of c. It's important to understand that limits is not what happens at c, rather what is happening to the function when it's getting very close to c. For example, here, you might have a hole, but you don't mind about that. What you realize is the important thing is that where it's approaching. That's why we're using that wording, approaching, okay? So let's look at this example that we have over here. So you can see that here we have the arrows, okay? So the limit is going to be whatever value is here at c, so the limit is L, okay? So if this is my function f, I know that the limit when x approaches to c of f of x is going to be equal to L. So this is the output, okay? So let's look at this example. If we want to estimate the limit when x approaches to 2, let's say, okay, of x minus 8 divided by x squared plus 4 by completing a table, okay, and we're going to verify with a graph, what are you going to do? Okay, so first approach, you can plug the 2 here, okay, and get a number, okay? But since they are telling you that you need to use a table, okay, we're going to plug these values, okay? I'm going to start with this 2. When I plug this 2 in my calculator, okay, you have that this is 0.752. This one over here, when we plug it in, we have that this is 0.749. As you can see, these two values are pretty close, but they are not the same. Let's plug this 2 in the calculator, okay? When I plug this one in the calculator, it gives me that it's negative 0.751. This one over here, it gives me that it's negative 0.749, okay? So again, they are getting closer, but they are not the same, okay? So then I plug it back again in my calculator, okay? And I put that this one, it gave me the same value here. And over here, I got that this is equal to negative 0.75. Okay, so you can see that it's getting closer and closer to what? Negative 0.75. Using our table, we can conclude that this is going to be equal to negative 0.75, or as you can imagine, in fraction notation, 3/4, negative 3/4, okay? So what we're going to do here, okay, is you can use a table, or you could also plug the number 2 here, okay? If you have the 2, what do you have? Let's do it over here. Okay, you have that the limit, okay, I'm going to write here, the limit when x approaches to 2 of x minus 8 divided by x squared minus 4, that's going to be equal to 2 minus 8 divided by 2 squared minus 4, okay? So this one, it gives you that it's plus. Okay, so this one will give you that it's going to be what? Negative 6 divided by 8, which we can simplify to what? Negative 3/4. Okay, so we can check that this is true with algebra. Okay, so you can do it via table and algebra. Let's do some examples here. Okay, you can either use the table or just use, your information from pre-calculus and algebra 2 when you just plug it in. Okay, so this one you can just replace the x with the 4, and you would have that it's 3 times 4 minus 2, and you have that this is going to be equal to 10 because you have that it's 12 minus 2. Okay, so I want to do this side because these are pretty similar to the previous ones. Okay, so over here what you have is when you plug the negative 3 here, you are going to have a number. Okay, and we're going to deal with more special limits later. Okay, so when we plug this one, wow, what do you have here? Okay, this one, okay, sadly, we cannot conclude. Why? Because we have a 0 over 0, and this is what I wanted to have. Why? Because here we cannot conclude. Okay, so when we have a 0 over 0, we cannot conclude. Therefore, what are you going to do? You need to factor. Okay, so you have that the limit when x approaches to negative 3 of this equation, you know that you can factor this via the sum of cubes. Okay, so you have that it's going to be x plus 3 x squared minus, and you have that it's going to be 3x plus 9, everything divided by this that you can also factor. Okay, you know that the factors of that one are x minus 3, x plus 3. The great thing is that you can cancel these two factors, and then you can plug the negative 3 into your remaining equation, meaning now we have this part. Okay, we have the limit of this part, and we're going to put a plus, but it's not, it's a minus 3x plus 9, and then you divide by x minus 3. Okay, so now when you plug it in, you have that this is going to be negative 3 squared minus 3 times negative 3. Okay, then plus 9, everything divided by negative 3 minus 3. And you have that this is going to be negative 9, negative 9, 9. Okay, and this is going to be negative 6. So you have that it's negative 9 over negative 6. Okay, are both of them negative? No, this is positive, sorry. Positive, and this is going to be, you simplify and you have that this is going to be negative, negative, is it, negative 3 over 2, I believe. Okay, so let me see. Yeah, I think so. Okay, so that's what we have. Okay, so after that, you're going to have problems like this one. If you just plug the 1, you again have a 0 over 0, so we cannot conclude. So what you're going to do in this equation is you are going to rationalize. Okay, so you have the limit when x approaches to 1 of 1 minus 1 root x divided by 1. You are going to rationalize. Okay, and this is the way that we can rationalize this problem. Okay, so what I recommend you to do here is do not distribute where you don't have one of the square roots, meaning I would leave it like this, the top, and then you can distribute here, x times x, you know that it's x, and then the middles will eliminate because you know that that's a property that you learned in algebra 2, okay, and minus 1. So you cancel this with this, having the limit when x approaches to 1, okay, of what? Square root of x plus 1, which is going to be equal to 2. Okay, and that's what we have for this type of problems. Okay, so you have those. Okay, so this is just the beginning of limits, and yeah, I hope that you enjoy the beginning of limits with basically just plug them in, see the indetermination, and also looking at limits using tables, okay? And the definition of limits, okay? I don't know if you have any questions, concerns. Yeah, just let me know if you have any questions or concerns. So please remember, if you have any questions or concerns, you can contact Momentum Learning. We give you the data so you can see the data here of the PowerPoint. Okay, so let me share it with you. They are open Sunday through Friday from 11 a.m. to 5 p.m. Central Time. And yeah, you can send them an email to info@momentumlearning.org for fast responses. They are quite fast answering. So if you need something or you have questions, just let them know, okay? I don't know if you have any final questions or concerns, please let me know. Okay, so yeah, thank you for stopping by, and yeah, I hope to see you during this semester. Thank you so much.